Welcome back, students, to our Chemistry 1510 video notes. In this section, we are going to talk about measurement and introduce ourselves to significant figures. So first, let's remind ourselves about two things that we should have some background in, precision and accuracy. So when we talk about precision, a lot of times this is defined as how close a set of values are to each other. And let's say they're measurements. And accuracy is how close a measurement or set of measurements are to a true value. Let's say, or an average. It's to an accepted or true value. So before we talk about these with respect to actual numerical examples, let's look at them with respect to pictures. So if we're looking at these pictures, the bullseye here in the center, that's going to be our true value. So let's draw something that is both accurate and precise. So in this case, if I'm using three measurements, something that's accurate and precise would all have those three measurements right in the center. So accurate, meaning it's close to the bullseye, precise, meaning those measurements are close to one another. So something that's not accurate wouldn't be hitting the bullseye, but if it's precise, we would be repeating that measurement over and over. Something that's neither accurate or precise might be something where, you're not precise and also you're not accurate. Now, this last one, precise, but not accurate. I feel like I have this one already. Not accurate and precise. Precise, but not accurate. Yeah, I have this one already. This is just the opposite of this one. So I want to say not precise, but accurate. So in this case, what you would be expecting is, honestly, most students say it's not possible. But in actuality, the average of your targets or your darts can average out to something that's accurate, even though they are not precise. So something like this, what I see here is that if I kind of look at these three darts that I've thrown, they make a triangle. And the middle of the triangle is right around the middle of my bullseye. And so, or the center of my target. And so here what we have is something where if we visually average these three, we get something that's accurate because the average is accurate, but not at all precise because we're not being significant or, hitting the same spot every time. So this one's a little bit more unusual, but it is possible. So this is how we might visually define accuracy and precision. Now, as we start to move into actual numbers, we're going to focus a lot on precision. And as we move forward and we start actually measuring things, what we're going to find is that precision plays out in our measuring devices. So if we look at something like this nail here, what I'm going to do whenever I measure something is I'm going to look at my graduations that I have. And here I have graduations at every 1 centimeter. And then in addition to that, I have graduations at the tenths place, right? So I have like a 5.1, a 5.2, a 5.3, and so on. So if I'm looking at this nail and the tip of the nail is right around here, It's tough to do without zooming in, but we can probably definitely agree that we're at least at 5 centimeters, right? 5 centimeters is here. So I think we can all agree that we're at 5 centimeters. And then here's 5.1, 5.2, 5.3, 5.4. That one was a little off. And maybe you think we're at 5.5. Right? Maybe you think, maybe we're not at 5.5. Maybe we're just before 5.5. Maybe we're at 5.4. But the person who's thinking maybe we're at 5.4 is probably thinking, well, it's not really 5.4. We're pretty darn close. So I'm going to throw in an estimated digit there at the end. And so this is going to be our pattern. Whenever we have a measuring device that has these graduations, we're going to put down a digit for every graduation, and then we're going to have one estimated digit. And so the same thing is going to be true if you thought this was spot on 5.5. You're saying, I have a graduation at 5, I have a graduation at 0.5, and I am estimating the 0 that comes after that. That 0 is telling my reader that I think that nail is spot on 5.5 right there, right? So I'm saying I don't even need an estimated digit. Maybe you thought it was just a hair over. Maybe you thought it was 5.51 or 5.52. Again, you would have a digit for the ones place, a digit for the tens place, and then you'd have your estimated digit. So every measurement has uncertainty. And a precise measurement is something with relatively little uncertainty. So not only can precision be defined as how close a set of measurements are to each other, but in addition to that, if we're looking at a measuring device, we can talk about precision in instruments. So the more precise an instrument, the more digits it's going to have. And we'll call them certain digits for the time being. So more digits that we're certain of. And so here we're certain of these ones. And then we estimate these ones. So the uncertainty in measurements is that you're always going to have one estimated digit. You can't have more, you can't have less, so it's always one estimated digit. And if you have a very precise measuring device, then that estimated digit is something quite small, right? It's 100ths. That's pretty darn small. But if something is not very precise, maybe it's estimating in the tens place or in the ones place. So your uncertainty can also be written like this. We can see it be written as plus or minus 0.01, which is the uncertainty for this particular measuring device. Because this measuring device is able to get the majority of the measurements that people would normally take to be within 0.01 centimeters of each other. So that's our uncertainty. Now, instead of reporting an uncertainty every single darn time, which trust me is obnoxious, what you're going to do is you're going to learn about significant figures or significant digits. So your significant digits are all digits in a measurement that are all the certain ones plus the final uncertain one, right? So it's all your certain digits plus your estimated digit. Now, when you go ahead and you read your balance is automatically going to give you, if the balance is digital, that is automatically going to give you the last digit is the uncertain estimated digit. So if you have a balance and your balance is reading, 1.392, this is automatically the estimated uncertain digit. So you don't have to do a lot with balances. But for rulers and graduated cylinders, you need to do a little bit more work. You read all the digits that you're certain of, all the ones that are associated with a graduation that are written on the measuring instrument, and then you estimate one more. So I want you to take a moment. I want you to look over here and determine what you think. How many milliliters do you think are showing in this graduated cylinder? So take a moment and report your number of milliliters down here, and then we're going to compare. All right, I'm ready to compare if you are. So you should get something around 43.0. If you didn't get 43.0, that's fine. You should have gotten something like 42.9 or 43.1. Those would be appropriate. If you just did 43, then you don't have an estimated digit, right? We're certain of the 4 because that's a graduation that's showing up right there. We're certain of the 3 because the bottom of the meniscus is hitting that third place, right? So here's your 40 graduation. Here's your 3 graduation. And now we need one more digit. We need the digit that we're uncertain of, the one we're estimating. So we have an estimated digit in all of those locations. 43 isn't enough. You need one more digit there. All right, that is enough for this video. I'm going to go ahead and send you over to Tyler DeWitt on YouTube, who is going to give you more details about significant figures and show you how they work in calculations. Then I have a practice sheet for you to work on with those, and then you'll come back to me and continue working on this note packet. Thank you so much for your attention. This is Katoni signing out.